In this video, we'll introduce some of the ideas behind using experiments to collect data. Experiments are the gold standard, allowing us to make causal conclusions. They allow us to consider questions such as, if I observe fewer infections in a group that wasn't vaccinated versus a group that was, can I conclude that it was the vaccine that caused the lower infection rate, or could it be something else? Or say a new teaching method results in better learning outcomes. Can I definitely attribute the improvement to the new method? We'll start by introducing some of the vocabulary that is used in experiments. The outcome, or response variable, is the variable that we are interested in, measured on each of the individuals or entities participating in the study. It is sometimes called a dependent variable because we are typically interested in how it depends on the values of the other variables, which are the explanatory variables. Explanatory variables, or predictors, or independent variables, are variables that we believe affect the response. The key feature that separates an experiment from an observational study is that in an experiment, the researcher manipulates the explanatory variables to see the effect on the response variable. An example of an experiment that we've already seen is the Patricia study to examine the efficacy of a vaccine at preventing infections with HPV. In the Patricia study, we were interested in whether or not the subject in the study acquired an infection, so that is our response variable. Response variables can be categorical or quantitative. In this situation, we have a categorical response variable with two categories. Yes, the subject acquired an infection in the study period, or no, they did not. In this example, the explanatory variable is also categorical. We believe that getting the vaccine affects the chance of getting an infection, and the explanatory variable is the vaccination status, with possible values yes or no. In an experiment, the investigator observes how a response variable behaves when he or she manipulates one or more explanatory variables. Since there are only a finite number of values of the explanatory variable that the researcher can possibly study, explanatory variables in experiments are typically categorical and are called factors in this setting. The values of a factor that are studied in an experiment are its levels. In our HPV vaccine example, the factor is vaccination status with levels yes or no. A particular combination of values for the factors is called a treatment. When there is only one factor, as in the HPV study, the treatments are the levels of the factors. But it's also possible that an investigator might want to simultaneously manipulate two explanatory variables to see the effect on the response. As an example, imagine a study comparing two drugs, we'll just call them drug A and B, each at two different doses, high and low. Then in this situation, we have two factors, each with two levels, but four different combinations, drug A in high dose, drug A in low dose, drug B in high and low dose. So in this case, there are four treatments. In experiments, the participating subjects or individuals are called experimental units. Sometimes treatments are given to groups of people or things, like all of the students in a class receiving a new teaching method, or all of the plants in one pot receiving a new type of fertilizer. The experimental unit is then not the individual student or plant, but the whole class or pot. Using this vocabulary, the key feature that separates an experiment from an observational study, again, is that in an experiment, treatments are imposed on experimental units by the researcher so that the effect of the treatments on the response can be seen. Extraneous factors are factors that are not of interest in the current study, but are thought that they might affect the response. They need to be controlled to rule out the possibility that the extraneous factor is causing any observed differences in the response. To control for an extraneous factor, we have a couple of different options. The first option is to hold it constant. Say we think that the HPV vaccine might work differently on males and females. We can then make the decision to say study only females. If we think it might work differently in different age groups, we could choose to study only one particular age group. This limits the generalizability of the study, but it also eliminates the potential of having the extraneous variable confound the results. The second method of controlling for extraneous factors is to use blocking. A block is a group of experimental units that are similar in the extraneous factor, and all treatments are randomly assigned to experimental units within each block. If we wanted to study the effects of the vaccine, and we wanted to include different age groups which might have differential response, we can treat age group as a block and randomly assign treatments within each age group. So in each age group, we have subjects who both receive the vaccine and do not receive the vaccine. But what about extraneous factors that can't be controlled? And even more of a concern, what about the extraneous factors that haven't been identified, just because we missed something, or perhaps because there are potential extraneous factors, maybe a genetic mutation that hasn't yet been studied, so we don't know that it's an extraneous factor? The solution is to use randomization. By randomly assigning individuals to treatment groups, we can ensure that any differences that exist between the groups in any possible extraneous variables are just due to chance. And the fact that we expect to see some differences due to this chance variation is part of our statistical model. After randomization, when we average out this chance variation, the treatment groups are essentially the same. Once we have a randomized experiment to compare treatments, we have a study for which, if we observe differences among the treatment groups, we can conclude that it was the different treatments that caused the difference in the response. The idea here is that we've eliminated any other differences between the groups. So if the response variable is different, the only explanation is the different treatments, and cause and effect conclusions can then be made. There are three fundamental principles of experimental design. Control the identified extraneous variables by blocking or holding them constant. Randomly assign experimental units to treatment groups. And use replication. We haven't talked about replication yet. And here I'm not talking about replicating an experiment to check whether a result found in one study also holds when you do another study. While this is an important part of the scientific process, we're currently only talking about single studies. So what I mean by replication here is that we need to apply each treatment to more than one experimental unit. Having replicates allows the researcher to estimate variability in the measurement of the response, which we can't do if we only have one observation for each treatment, and ensures that the treatment groups are more comparable in values of the extraneous factors by having the opportunity to have different values of the extraneous factors within each treatment group. The word control also has another meaning in experiments. Experiments often have what we call a control group. If the goal of an experiment is to show that a treatment affects the response, you need to have at least one other group for comparison. It's possible that the simple act of studying an experimental unit causes it to change. Studying at least two groups undergoing the same experiment allows us to compare them under the same circumstances. A comparison group in a study could get a different treatment or no treatment. It is called a control group if it either does not receive a treatment or receives the current standard treatment if there is one. The control group is itself a treatment group, and if there is only one factor, control is considered a level of the factor. So the only way to establish a causal relationship is to carry out a randomized, controlled experiment. So why would anyone carry out a study that's not an experiment? The answer is simple. It's just not always possible for ethical or practical reasons. If we want to study the effect of smoking on human mortality, we can't randomly assign some people to smoke a pack a day and some people not to. That would be unethical. For studies on humans, we need to have sufficient doubt about the benefit of a treatment, that we do not feel that we are unfairly exposing some of the subjects to an inferior treatment in order to carry out an experiment. If we're interested in how the explanatory variable GDP affects the response of life expectancy for countries, we can't manipulate the GDP of a country, so carrying out an experiment is not practically possible. Let's look at one more example of an experiment. This story is slightly adapted from a project presented by 2 Montreal students at the 2011 Canada-wide Science Fair. This project was the winner of the Statistical Society of Canada Award for Excellence in the Use of Statistical Methodology, which they won for their excellent example of a well-designed experiment. The students were interested in ischemic preconditioning, which is a technique to create resistance to loss of oxygen through loss of blood supply to tissues. Ischemic preconditioning works by applying brief episodes of restricted blood flow in order to protect against damage from a subsequent longer-term episode. The students were interested in whether a similar technique could be used to improve sports endurance. They provided ischemic preconditioning using a blood pressure cuff. They applied a pressure of 20 pounds to some of their subjects and, for comparison, minimal pressure, nominally 0 pounds, to other subjects. They also compared applying the pressure for 10 minutes versus 20 minutes. So there were a total of 4 treatments, the 4 combinations of the 2 pressures and the 2 lengths of time applied. Each treatment was applied to 10 teenage males, so there's our replication. Since there are 4 treatments, there were 40 participating teenagers, and these are the experimental units. They were chosen to be of similar athletic ability. After application of the treatment, the length of time the teenagers could stay in a wall squat position was measured. This is the response. Note the use of a control group here. The students needed to know if ischemic preconditioning worked, so they gave a sham treatment of 0 pounds to some of their experimental units, some of whom got 0 pounds for 10 minutes and some for 20 minutes. Moreover, to control for extraneous factors, only a specific group of people were studied, namely, male teenagers of similar athletic ability, chosen because they participate in sports at school. Although this wasn't done, another way they could have controlled for extraneous factors was to use blocking. For example, they could have enrolled both athletes and non-athletes in the study and assigned the 4 treatments to subjects within each of the athletic groups. Another of the principles of experimental design is randomization, and the 40 experimental units were randomly assigned to which of the 4 treatments they received. This ischemic preconditioning experiment also illustrates some other characteristics of excellent design, which should be used when appropriate and possible. The students used blinding. Blinding, if it can be used in an experiment, reduces the potential for bias, since people don't know if a treatment is in place or not. Subjects can be blinded, meaning they don't know which treatment they received. The person measuring the response can also be blinded if he or she does not know which treatment was given to which participant. Experiments can be single-blind, meaning only one type of blinding was used, or double-blind if both types of blinding were used. The ischemic preconditioning experiment was single-blind. Subjects did not know which treatment they received. And they used a placebo. People often show change when participating in an experiment, whether or not they receive a treatment. This is known as the placebo effect. For this reason, the control group is often given a placebo, which is something that is identical to the treatment received by the treatment groups, except that it contains no active ingredients. So the subjects aren't aware of whether or not they're receiving a treatment. In our ischemic preconditioning experiment, the placebo was the application of 0 pounds pressure to some of the experimental units. Randomization plays 2 key roles in data collection. This table summarizes those 2 roles. By using random sampling, we get a representative sample and ensure that we can generalize our results to a larger group or population free of any selection bias. Later on in our inferential procedures, we'll use a statistical model that accounts for the random variation that causes our sample to differ from other samples that we could have possibly chosen in another random selection. Randomization also plays a key role in experiments. Randomly assigning experimental units to the treatments they receive eliminates the effects of extraneous factors, allowing us to make causal conclusions. While the extraneous factors may vary from treatment group to treatment group somewhat, randomization ensures that these differences are due to chance variation only and not any systematic difference that could confound our interpretation of the effect of the treatment. So if we want to make causal conclusions that we can generalize to an entire population, we need to randomize both in our selection of our experimental units and in assigning treatments to experimental units.